We've been talking about thermochemistry, and we already defined some basic terms, and last time we got into calculating heat transfer, and we saw that in our do now, because we know that Q, heat transfer, is equal to MC delta T, nice little rhyme there, and we identified all the variables as well as their units. And if you will please do chemistry with quantities, many more of you will be successful calculating different quantities. And as I said from last time, this is the classwork that goes with that. The first thing we want to look at today is how to calculate heat transfer when a substance undergoes a phase change, and we will also discuss principles of calorimetry. Later in the week we'll get into enthalpy, entropy, and free energy, understanding what they are as well as calculating those quantities. Today, first up, is calculating Q, heat transfer when a substance undergoes a phase change. And we've looked at this type of heating curve before, shown here. And we know that if we plot temperature on the y in degrees Celsius versus time on the x in minutes, we can generate a heating curve. And this is something we used to do in the lab, although it's not exactly stimulating. You can start out with a block of ice and you can melt it, and then you can continue heating it so that the substance vaporizes to generate steam. What you do see when a substance undergoes a phase change, for example, if this is water, 0 degrees Celsius and 100 degrees Celsius, the substance will melt here and will boil here. And what can you say about the change in temperature when the substance either melts or boils? Delta T in both instances there will be 0. So when a substance undergoes a phase change, delta T will be equal to 0. And that poses a problem, because if we go back here to Q is equal to MC delta T, when the substance undergoes a single phase change, not multiples, because you'd have to take into account this ramp here, if you will, when you've got liquid, delta T is 0. So Q in that case would be 0 if we use this formula. But when substances undergo boiling, melting, freezing, vaporization, etc., they do undergo heat transfer. So we're not going to use this formula if we have a phase change. You'll use this formula if you do see the substance undergoing a change in temperature, final minus initial. When you undergo a phase change, you can use one of two formulas. You either can use Q is equal to m the mass times delta H of fusion, and you'll use this formula for melting or freezing. Melting, the delta H of fusion is positive. For freezing, it is negative. We'll talk a little bit more about that in a minute. Or alternatively, you can use Q is equal to the mass times the delta H of vaporization, and you'll use this when the substance is either boiling or vaporizing, again positive, or when the substance is condensing, negative delta H of vaporization. The delta H of condensing is equal to but opposite that of vaporization, so equal but opposite in sign, giving rise to positive Q's for boiling or vaporizing, negative Q for condensing, and similarly positive Q here, negative Q here. What you will also see, and this will make a little more sense as we continue on into the lesson later in the week, is you will find as you go from solid to liquid and liquid to gas in this direction, you'll see that the reaction is endothermic. So again, melting, boiling, heat will be absorbed, and in contrast, as you go in the reverse direction, this will be exothermic, where heat is released, and again, this will be condensing, and this will be freezing. And we'll talk more about endo and exothermic reactions probably tomorrow. So two formulas. You've got Q is equal to mass times delta H of fusion for freezing and melting. Q is equal to M delta H of vaporization for boiling, condensing, vaporizing, etc. And those heats of fusion and heats of vaporization can be found on the back of your periodic table in table 6. 6 substances listed. Heat of fusion in joules per gram. Remember, the degrees Celsius factor is not included here because the delta T would be 0, so we're using a different variable. Heat of vaporization is here. If you compare heat of fusion to heat of vaporization for each of these substances indicated, which one is larger, heat of fusion or heat of vaporization for the same substance?
Vaporization.
Heat of vaporization, clearly a larger quantity than the heat of fusion. And we mentioned this briefly when we talked about it, and you'll see this in your notes. I'm going to slide down just for a sec because there's a better heating curve shown here. You'll see it takes much longer to vaporize 1 mole of liquid water than it does to melt it, and that's because all of the intermolecular forces need to be broken, and that will take more time than just some of them being broken here. And you don't want to allow for the reformation here either. And again, when a substance undergoes a phase change, the change in temperature is 0. These types of problems are very, very simple to do. You will have no difficulty with this, provided that you remember melting and freezing with fusion, boiling, vaporizing, condensing with delta H of vaporization, and then it'll be very simple. Also, if you're unsure of melting or freezing, typically I just remember it this way. You've got melting and endo and men. They will often warm your heart. Positive, not always. Negative. Okay? And you can come up with whatever it is you want. But again, along this line, positive delta H's. Along this line, negative delta H's. And we'll talk more about delta H next time. So let's take a look at these simple problems. We've already gone through the basic structure of it. We know what vaporization is. Heat of vaporization is how much heat must be absorbed to vaporize 1 gram of a liquid. So once you know what your substance is, you will find its delta H of vaporization and multiply it by the mass that's provided. No change in moles necessary. In the first example, it says calculate the heat required. So you're calculating Q. You've got an 120 gram sample of liquid ethyl alcohol. You need to know what it is. You want to change the liquid into vapor, so you're vaporizing at constant temperature. So what we've got in number 1 then, we want to know Q. The mass is 120 grams. The delta H of vaporization, because you're vaporizing it, of ethyl alcohol, if you look in table 6, you'll see that ethyl alcohol has a delta H of vaporization of 879 joules per gram. Q is equal to M delta H of vape, and once you've got all the pieces, you just need to plug and chug. Watch your sig figs here. You've got 120 times 879. What pops out of the calculator is this, but you want 3 sig figs. That would be that, or you could do 1.05 times 10 to the 5th joules, or if you wanted to, you could do 105 kilojoules. Any of these will earn you full credit. This will be a loss of 1 point for sig figs. And again, they told us that we were vaporizing, we were going liquid to vapor, so we knew delta H of vape. In the second problem, it says how much heat is released when 25 grams of steam at 100 degrees Celsius condense. So they're mentioning condense, and they mention steam. So we're thinking water. Doesn't matter about the temperature. It's very interesting that water will boil at 100 degrees Celsius. Reverse process is condensation, but that quantity of 100 degrees Celsius does not figure into our problem. We've got mass delta H of vape, and in this case it's going to be negative because we want to condense. So we've got 25 grams. We look at water. What's the delta H of vape for water? 2,260 joules per gram. I am going to put a negative in there because we've got the reverse process. And that will be 56,500 joules. So vaporizing, boiling, condensing, delta H of vaporization. If you're melting or freezing, you'll use the delta H of fusion. Questions here? Easy peasy? The other problems deal with delta H of fusion. I think you will find these equally as straightforward. Changing from solid to liquid is melting. Delta H of fusion, if you freeze, you just use the negative of it. This is how much heat is needed to cause 1 gram of a solid to melt into its liquid phase. Formula, as we've mentioned. Calculate the heat required. We're going to melt a 25-gram block of gold. The melting point of gold is 1,064 degrees Celsius. Very interesting in regard to what the temperature is at which gold melts, but not included in our calculation. So on this problem, what we've got we want to know Q. The mass is equal to 25 grams. And the delta H of fusion for gold, AU, is 64.5 joules per gram. Q is equal to M, delta H of fusion. We've got 25 grams times 64.5 joules per gram. And in 3 sig figs, we've got 1,610 joules. And I just want to slide back up for a sec. On this one, they asked how much heat is released. So it is 56,500 joules, but it's probably easier for you to carry that negative so you're clear. We had this because we were condensing, so you really do want that negative there as well. And let's pull the information out on this one and see if you can do it. It says calculate the heat required. So again, going after Q, we want to freeze a 30-gram block of water. Give it a shot. How'd we do? Awesome. So you'll see one like the problem we did last time and one like one of these. But again, just be careful. Are you freezing? Are you melting? Are you boiling? Are you vaporizing, condensing? Once you know what you're doing, then you'll know what formula to pick. The last thing we want to look at today will involve combining several concepts together. It's not difficult if you follow the steps, but one thing I did notice on the last test is that some of you are not doing enough practice problems, so you're unable to execute on game day. Practice makes perfect, and if you do a lot of practice problems, you'll be highly successful when you do this type of problem solving on any assessment. Flipping back to your notes, already mentioned this heating curve previously, and we have discussed it. We're not going to be looking at melting and boiling point from delta H's of fusion and vaporization, so I've scratched that out. What we will be looking to do here is measure changes in energy. And the first thing we want to look at is how we can measure values of specific heat, heats of vaporization, and or heats of fusion using a technique known as calorimetry. The instrument that we use is a calorimeter. So let's diagram this out. It's all written out, but who wants to read all that gibberish. We're going to keep it really simple. So let's say we had a calorimeter. And that's essentially two nested styrofoam cups, and you will nest them to provide better insulation. Your lab, this is actually the lab we used to do, but the kids found it to be very tedious, so I've got a much more fun lab for you where you will determine the caloric content of potato chips or some other junk food that you tend to consume too much of, with the exception of nuts. No nuts, no peanuts. In any event, in this inside cup, you will have water. You will know the mass. You will know its initial temperature. The specific heat of water is 4.18 joules over grams degrees Celsius. So you will know all of that. You will put a metal or unknown substance in that water, and again, you'll know the mass of the metal, put it on the balance, get the mass. You'll know its initial temperature, and very often you will be looking for the specific heat of the metal. You will have a stir bar in here so you can stir it up, and you will also have a thermometer in here so that you can measure the temperature first of the water and then of the solution. One thing that we mentioned early on is that energy is conserved, law of conservation of energy, and what you're going to see is any heat lost by the metal, because typically it's red hot, will be equal to but opposite to the heat gained by the water, because the water will warm when heat is transferred from the hot metal or unknown substance to the cooler water. These will be equal but opposite, negative in sign. Now, when heat is transferred from the hot metal to the cool water, ultimately the temperature will stop changing, and the temperature that you finally reach will be the final temperature for both. So when the temperature stops changing, when you no longer see a change in temperature, you will have the final temperature for both. And as a result, we can walk through these types of problems in 3 steps. And that's what we're going to be looking at here. I'll walk through the first example with you very slowly so you can follow. In the first example, it says a 24-gram sample of a metal is at 75 degrees Celsius. So the first thing I'm going to do is get some information down about the metal. The mass of the metal is 24 grams. The initial temperature of the metal is 75 degrees Celsius. It's placed in a calorimeter containing 25 grams of water at 20 degrees Celsius. So in regard to the water, the mass is 25 grams and its initial temperature is 20 degrees Celsius. The temperature stopped changing at 29.4 degrees Celsius. So the final temperature is equal to 29.4 degrees Celsius. We want to calculate the specific heat of the metal. We know that the specific heat of water is 4.18 joules over grams degrees Celsius from table 3. We also want to identify the metal. And if you're organized as you get the information down and you follow the 3-step process I'll show you here, you will be highly successful. In step 1, we're going to calculate the Q of the water, which is equal to MC delta T, all of the water information. The mass of the water is 25 grams. The specific heat of water is 4.18 joules over grams degrees Celsius. Delta T is the final minus the initial. So the delta T for water is 9.4 degrees Celsius. And in 3 sig figs, actually make it 2 sig figs, because when we subtract we maintain decimal places. So in 2 sig figs then, we've got a Q of water of 980 joules. In step 2, we want to calculate the Q of the metal, and that's going to be the negative Q of the water, because any heat lost by the metal will be gained by the water. These will be equal but opposite in sign. So the Q of the metal is negative 980 joules. Again, equal but opposite in sign. And then finally in step 3, we want to calculate the specific heat of the metal or unknown substance. I know that Q is equal to MC delta T. The specific heat of the metal is equal to Q of the metal over the mass times the change in temperature. I've got negative 980 joules. The mass of the metal is 24 grams. And be careful here, the delta T of the water, I'm going to slide this back down so we can figure it out. T final minus T initial right here. The delta T of the metal is this minus this. And that's negative 45.6 degrees Celsius. And again, don't make a calculator error. The only parentheses you need in the calculator are those in orange. And I get point, when you round, 90 joules over grams degrees Celsius. And then in terms of the identity, I look at table 3 and which substance is closest to a specific heat of 0.90. Aluminum. Say it again.
45.6.
29.4 minus 75. And so that's negative. The two negatives cancel. You cannot get a negative specific heat. Those negatives will cancel. You'll have a negative Q of the metal or unknown and a negative delta T because the metal's losing heat. Aluminum. All right, let's take a look at the other example. It's written very similarly. We'll pull the variables out and we'll see if you can do it. In number 2, it says a 15-gram sample of a metal or unknown substance at 110 degrees Celsius. I immediately get that information down, a metal or an unknown, that's UNK for unknown. The mass is 15 grams. The initial temperature is 110 degrees Celsius. That's a big fat decimal point. It just came out that way. It's placed in a calorimeter. We've got water. The mass is 7.654 grams. The initial temperature of the water is 30 degrees Celsius. The temperature stopped changing at 50 degrees Celsius. That's the final temperature for both. We want to know the specific heat of the metal, the specific heat of water is 4.18 joules over grams degrees Celsius. And we also want to know the identity. You'll follow the same 3-step procedure. You may want to get the delta T's out initially. It might be easier for you to grab them from the beginning. Follow that. You want to do it together? You want to do it yourself? Together? Okay. Let's get those delta T's. Final minus initial for the water is 20 degrees Celsius. Final minus initial for the metal is negative 60 degrees Celsius. No decimal point there because that one has nothing after it. So nothing after the decimal point. If you want to keep it there, that's fine. It might be easier for you. In the first step, we want to calculate the Q of the water. That's MC delta T. Take a minute to calculate the Q of the water. So we'll do it together, but you're going to do pieces to make sure you've got it. And what'd you get for the Q of water? I got 640 joules. So if that's the Q of water, in step 2, the Q of the metal is equal to negative Q of the water. And then in step 3, we want to calculate the specific heat lowercase c of the metal. Do you think you can try it from there? Yes, yes?
Yep.
All right. Try and pick it up from there. How we doing? Who's got an answer? What'd you get?
Wait for I got 7.711.
But we also want to make sure we have units because we've got quantities. So what we've got here, as such, 0.71 joules per gram degree Celsius. This was in 2 Siggy Wiggies. That's carbon. You have to specify graphite because we also have diamond that has a lower specific heat. And that's how you figure out the specific heat as well as the unknown substance. You can do this with delta H and delta fusions. We're not going to do it. You'll see one problem like this, and if you follow this 3-step procedure, you will be very successful. In your classwork, you can do most of the crossword puzzle at the top. Couple questions you probably won't get yet. Don't panic. You'll get them toward the end of the week. And in the classwork, you can do numbers 1 through 8. 7 and 8 are like these problems. 4 through 6 are like what we did at the beginning. 1 through 3, similar to what we did last time. So that's a brief introduction to heat transfer. We'll get into very simple enthalpy calculations, which is as far as the quiz will go. And we'll discuss your quiz date later in the week. Questions?